Hi, everyone. So this time we're going to go over an application of orthogonal diagonalization to give you a reason why you would want to learn it. The difficulty we have is that a lot of the interesting applications of orthogonal diagonalization requires topics that you may not know yet. So I'm kind of restricted to the type of things we can do. I'm going to therefore look at something I'm fairly certain you would have seen in pre-calc, which would be graphing conic sections of ellipses and of parabolas and hyperbolas, and talk about how to graph them even more generally than what you learned back then. So that has to do with what's called quadratic forms. Now, there's lots of things connected to quadratic forms. There's at least 3 or 4 different topics I can go off on with quadratic forms. I'm going to focus just on the graphing ones. So here we go. You need to know what a quadratic form is. A quadratic form is just a function on n variables. So it can be written as x transpose times a matrix A times x, where A is a real symmetric matrix. So that has to be a real symmetric n by n matrix. And the vector x is just a vector of real numbers. We refer to the matrix A as the matrix that's associated with the function. It's associated with the quadratic form. Just want to make sure you understand what we mean by that. So I want to know what quadratic form is associated with the matrix you see here. Well, it's just a matter of writing down the multiplication. So the multiplication, the function would then be x transpose. We'll assume x is the vector xy. So that transpose would be a row vector, xy, times AB, BC, times the column vector xy. And then just go ahead and do that matrix multiplication. I took the matrix and I multiplied to the vector xy. When you go ahead and do this much of the product, you get that product right there. And then we have a row times a column. We just do the multiplication and just add it up. You then get this particular quadratic form. Notice the quadratic form has x squared in it, has y squared in it, but it also has a cross multiplication term, x times y, which you're very likely have not seen very often at all. Also notice that this number here is a b, and yet what pops up here is 2b. We can therefore reverse engineer this, and if I give you a quadratic form already multiplied out, I can figure out then from that what would be the matrix associated with it. Let's do that. So here is a quadratic form. This time, though, the vector is x1, x2, x1, x2. And it's 7 times x1 squared minus 6 times x1, x2 plus x2 squared. I want to write that in quadratic form. So that means I have to have a matrix that does it. Well, that matrix has to be the upper left-hand corner, first row, first column has to be 7. The lower right has to be first, second row, second column would have to be 1. And since the cross multiplication term, x1 times x2 is -6, and that's 2b, then b has to be -3. So the off diagonals are -3. That's it. That would then have to be the quadratic form written in matrix form. Now, just to make sure you understand one more time, let's go ahead and evaluate this function 2 different ways. One's by just the formula, and the other is by the matrix multiplication. So if I wanted to find out then what would be the function f at 1, 2, it's just 7 times 1 squared minus 6 times 1 times 2 plus 2 squared. So that is 7 minus 12 plus 4. The answer is -1. It's not easy. We'll do it again, but this time as a function of the vector. And I'll write it this way in order to not go and put in the of notation. So it's the function of that vector. That would then equal, it's 1, 2 times the matrix 7, -3, -3, 1 times the vector 1, 2. That would then be 1, 2 multiplied by, now that would be a column vector. The first entry is first row times first column. That'd be 7 minus 6. That'd be 1. Then I'd have second row, first column. That'd be -3 plus 2. That'd be -1. And if I do that multiplication, you get a 1-by-1 matrix, which we can just associate with a number, and that's actually -1. Notice you get the same answer either way. Your first inclination is then, well, if we can do it both ways, why don't we just do it with the formula? Well, the reason is with this matrix format, we then bring to bear linear algebra because the matrix is symmetric and therefore orthogonally diagonalizable. And there probably is something neat we can do. So the neat thing is that this function in the current way of representing points in the standard basis method of I and J, E1, E2, has a cross multiplication term, x1, x2. I want to find a different system. And in that system, the function does not have a cross multiplication term because we can therefore figure out how the function behaves quite a bit faster if there just wasn't that cross term in it. That requires the principal axis theorem. Obviously, it must be important if it has a formal name. So every quadratic form, x transpose times a times x, can be converted into a much simpler form. All you have to do is change the variables. You use x equals q times y, where q just orthogonally diagonalizes a. Just to show you what I mean, just to do this multi-substitution. So x transpose times a times x is this weird quadratic function. It has x1 squared, x2 squared, x3 squared, has cross terms, x1 times x2, x2 times x3, who knows how many symbols. So, but if you replace x with q times y, you get that. If you simplify the transpose, you get this. But notice that you can reassociate the inner product. Q transpose times A times Q, that's the diagonal matrix. That's the matrix whose main diagonal is the eigenvalues. So that's that. But that multiplication is crazy easy to do. Y is a vector, y1, y2, y down to yn. And if you just do the multiplication, you get that. And notice there are no cross multiplication terms. You do not see a y1 times y2. There's no y1 times y5. There's no y2 times y3. There are no cross product terms at all. That's great. That's great. So you need to see then at least one application of it. One application of it. So that'll be then the next video in this sequence.